This is an article from Cloudflare on a blog. It's named How We Built Pingora, the proxy that connects Cloudflare to the internet. And they are also saying that they are going to replace the usage of Nginx, which is process-based, with Pingora, which would have a single connection pool. Let's get the details here on what is this exactly. Introduction. Today we are excited to talk about Pingora, a new HTTP proxy we've built in-house using Rust that serves over 1 trillion requests a day, boosts your performance, and enables many new features for Cloudflare customers, all while requiring only a third of the CPU and memory resources of the previous proxy infrastructure. As Cloudflare has scaled, we've outgrown Nginx. It was great for many years, but over time its limitations at our scale meant building something new made sense. We could no longer get the performance we needed, nor did Nginx have the features we needed for our very complex environment. So it was interesting to see that on these big companies, on these places where the scale is outpacing all other scales, they invented new solutions. So now they're replacing Nginx with Pingora, which is their own proxy. Many Cloudflare customers and users use the Cloudflare global network as a proxy between HTTP clients, such as web browsers, apps, IoT devices, and more, and servers. In the past, we've talked a lot about how browsers and other user agents connect to our network, and we've developed a lot of technology, implemented new protocols, Quick, and optimizations for HTTP2 to make this lack of connection more efficient. Today we are focusing on a different part of this equation, the service that proxies traffic between our network and servers on the internet. This proxy service powers our CDN, worker fetch, tunnel, stream, R2, and many other features and products. Let's dig in on why we choose to replace our legacy service and how we developed Pingora, our new system designed specifically for Cloudflare's customers' use case and scale. Why build yet another proxy? Over the years, our usage of Nginx has run up against limitations. For some limitations, we optimized our workers around them, but others were much harder to overcome. Architecture limitations hurt performance. The Nginx worker process architecture has operational drawbacks for our use cases that hurt our performance and efficiency. First, in Nginx, each request can only be served by a single worker. This results in unbalanced load across all CPU cores, which leads to slowness. Because of this request process spinning, because if one request is heavier than another and it's pinned to a process, then this process would be, this CPU core would be working much harder. So because of this request process spinning effect, requests that do CPU heavy or blocking IO tasks can slow down other requests. As those blog posts attest, we've spent a lot of time working around these problems. The most critical problem for our use case is poor connection reuse. Our machines establish TCP connection to origin servers to proxy HTTP requests. Connection reuse speeds up time to first byte of request by reusing a previously established connection from the connection pool, skipping TCP until a handshake required on new connection. However, the Nginx connection pool is per worker. When a request lands on a certain worker, it can only reuse the connections within that worker. So the problem is that a request lands on a worker and the worker is connected to some backend services. We'll see this immediately. When we add more Nginx workers to scale up, our connection reuse ratios get worse because the connections are scattered. It's like stateful. The workers are stateful and connected versus something more stateless where each request receives the whole pool of CPU. Connections are scattered across more isolated pools and of all the processes. This results in slower time to first byte and more connections to maintain, which consumes more resources and money for both of us and the customer. So we see here the diagram of the before. Before, we had here clients making requests to Cloudflare. Cloudflare has multiple connection pools. Multiple connection pools are connected to the backend services, and because so it's like stateful. This request is coming to this. As mentioned in the past blog post, we have workarounds for some of these issues, but if we can address the fundamental issue, the worker process model, we will resolve all this problem naturally. It's like moving from stateful to stateless. Some types of functionality are difficult to add. Nginx is very good web server, load balancer, or a simple gateway, but Cloudflare does way more than that. We used to build all the functionality we needed around Nginx, which is not easy to do while trying not to diverge too much from Nginx upstream codebase. This is also a good evolution because they first used the tools that already exist like Nginx, and only after gaining experience and utilize them to the end they move, for example, and not trying to early optimize. For example, when retrying failing over a request, sometimes we want to send request to a different origin server with a different set of request headers, but that is not something Nginx allows us to do, because the request is pinned to a connection and the connection pool is pinned to some servers. In cases like this, we spend time and effort on working around the Nginx constraints. Meanwhile, the programming languages we had to work with didn't provide help alleviating the difficulties. Nginx is purely in C, which is not memory safe by design. It is very error-prone to work with such third-party codebase. It is quite easy to get into memory safety issues, even for experienced engineers, and we wanted to avoid this as much as possible. The other language we used to complement C is Lua. It is less risky but also less performant. In addition, we often found ourselves missing static typing when working with complicated Lua code and business logic. And the Nginx community is not very active and development tends to be behind closed doors. Choosing to build our own. Over the past few years, as we've continued to grow our customer base and feature set, we continually evaluated three choices. 1. Continue to invest in Nginx and possibly fork it to tailor it 100% to our needs. We had the expertise needed, but given the architecture limitations mentioned above, significant effort would be required to rebuild it in a way that fully supported our needs. Migrate to another third-party proxy codebase. There are definitely good projects like Envoy and others, but this path means the same cycle may repeat in a few years. 3. Start with a clean slate, building an in-house platform and framework. This choice requires the most upfront investment in terms of engineering effort. We evaluated each of these options every quarter for the past few years. There is no obvious formula to tell which choice is the best. Okay, so I love this visibility because it's true. There is no obvious formula to tell which choice is the best. For several years, we continued with the path of the least resistance, continuing to augment Nginx. However, at some point, building our own proxy return on investment seems worth it. We made a call to build a proxy from scratch and began designing the proxy application of our dreams, the Pingora project, design decisions. To make a proxy that serves millions of requests per second, fast, efficient, and secure, we have to make a few important decisions. We choose Rust as the language of the project because it can do what C can do in a memory-safe way without compromising performance. Although there are some great off-the-shelf third-party HTTP libraries such as Hyper, we choose to build our own because we want to maximize the flexibility in how we handle HTTP traffic and to make sure we can innovate on our own pace. I think Cloudflare is going to become super huge. I mean, They are now building their own proxies, their own HTTP parsing. At Cloudflare, we handle traffic across the entire Internet. We have many cases of bizarre and non-RFC compliant HTTP traffic that we have to support. This is a common dilemma across the HTTP community and the web, where there is tension between strictly following HTTP specification and accommodating the nuances of a widely ecosystem, potentially legal legacy clients or servers. Picking one side can be a tough job. HTTP status codes are defined in RFC 91110 as a 3-digit integer and generally expected to be in the range 100 through 599. Hyper was one such implementation. However, many servers support the use of status code between 599 and 999. An issue had been created for this feature, which explored various sides of the debate. Now they are explaining why they are building their own HTTP library, because not all HTTP clients and servers supported exactly what happens in the RFC, which limited the HTTP status codes to up to 599. While the Hyper team did ultimately accept that change, there should have been valid reasons for them to reject such an ask, and this was only one of many cases of non-compliant behavior we needed to support. In order to satisfy the requirements of Cloudflare position in the HTTP ecosystem, we needed a robust, permissive, customizable HTTP library that can survive the wilds of the internet and support a variety of non-compliant use cases. The best way to guarantee that is to implement our own. The next design decision was around our workload scheduling system. We chose multi-threading over multiprocessing in order to share resources, especially connection pools, easily. We also decided that work stealing was required to avoid some classes of performance problems mentioned above. The Tokyo async runtime turned out to be a great fit for our needs. Finally, we wanted our project to be intuitive and developer-friendly. What we build is not the final project and should be extensible as a platform as more features are built on top of it. We decided to implement a life of a request event-based programmable interface similar to Nginx OpenResty. For example, the request filter phase allows developers, so it's like plugining and middlewares inside the request handling. The request filter phase allows developers to run code to modify or reject a request when a request header is received. With this design, we can separate our business logic and generic proxy logic cleanly. Developers who previously worked on Nginx can easily switch to Pingora and quickly become productive. Pingora is faster in production. Let's fast forward to the present. Pingora handles almost every HTTP request that needs to interact with an origin server for a cache miss, for example. And we've collected a lot of performance data in the process. First, let's see how Pingora speeds up our customer traffic over all traffic. Pingora shows 5 millisecond reduction on the median time to first byte and 80 millisecond reduction on the 95% percentile. This is not because we run code faster. Even our old service could handle requests in sub-milliseconds range. The saving comes from our new architecture. We can share connections across all threads. This means a better connection reuse ratio. So the connection is not pinned to a process, which spends less time on TCP and TLS handshakes. So we have multiple requests coming to a single connection pool. Across all customers, Pingora makes only a third as many new connections per request compared to the old service. For one major customer, it increased the connection reuse ratio from 87% to 99.92%, which reduced new connections to their origins by 160x. To present the number more intuitively, by switching to Pingora, we saved our customers and users 400 years of handshake time every day. More features. Having a developer-friendly interface engineers are familiar with while eliminating the previous constraints allows us to develop more features more quickly. Core functionality like new protocols act as building blocks to more products we can offer to customers. As an example, we were able to add HTTP2 upstream support to Pingora without major hurdles. This allows us to offer gRPC to our customers shortly afterwards. Adding this same functionality to Nginx would have required significantly more engineering effort and might not have materialized. More recently, we've announced Cache Reserve, where Pingora uses R2 storage as a caching layer. As we add more functionality to Pingora, we are able to offer new products that weren't feasible before, more efficient. In production, Pingora consumes about 70% less CPU and 67% less memory compared to our old service with the same traffic load. The savings come from a few factors. Our Rust code runs more efficiently compared to our old Lua code. On top of that, there are also efficiency differences from their architectures. For example, in Nginx OpenResty, when Lua code wants to access an HTTP header, it has to read it from the Nginx sys-struct, allocate a Lua string, and then copy it from a Lua string. Afterwards, Lua has to garbage collect its new string as well. In Pingora, it would just be a direct string access. The multi-threading model also makes sharing data across requests more efficient. Nginx also has shared memory, but due to implementation limitations, every shared memory access has to use a mutex lock and only strings and numbers can be put into shared memory. In Pingora, most shared items can be accessed directly via shared references. Okay, so this is becoming longer. I'm not sure we need all this. Conclusion. To summarize, we have built an in-house proxy. This is from Cloudflare, right? Pingora. To summarize, we have built an in-house proxy that is faster, more efficient, and versatile as the platform for our current and future products. We will be back with more technical details regarding the problems we faced, the optimization we applied, and the lessons we learned from building Pingora, rolling it out to power a significant portion of the internet. We will also be back with our plan to open source it. Woo! Pingora is our latest attempt at rewriting our system, but it won't be our last. It is also only one of the building blocks in the re-architecting of our systems. Okay, so this was Cloudflare switching from Nginx to Pingora. Very interesting. And moving to threads from processes. And you see, also Java has introduced recently, it's coming to release the virtual threads, which I discussed in a previous episode. So people are moving all the time from one architecture to another. In the past, it was from threads to processes. Now it's from processes to threads. But maybe this makes sense because every time we move from one architecture to another, over time we understand the computing world from another angle, and then we take a couple of angles from the new architecture to the old architecture, and then the old architecture we improve it and it becomes better. And this is how the world was about.